Okay, good morning. So, we have been discussing about different flow types based on their phase associations. For example, phase associations can be of liquid vapor, it can be gas solid, it can be liquid solid, and it can be combination of all. Okay, so in case of liquid vapor two phase flow, we have plenty of examples. For example, boiling, condensation, evaporation, all these comes under the category of liquid vapor. Okay, and in case of gas solid, particularly we found its applications in say fluidized bed reactors, our boilers when combustion of the coal is taking place and fly ash particles are getting mixed with the air. Then in order to transport the fly ash in the thermal power plants, we use say pressurized gas to carry the particles, and there we can have two types of associations. One is actually dilute phase uh, gas solid two phase flow, or it can be dense. So in case of dilute, the particles will be suspended in the fluid medium and the particle interactions are not important. On contrary, in case of dense phase flow, particles are closely interacting with each other. These are kind of overlapping over each other. So there will be particle interactions important, whereas the gas which is occupied between the particles in their void spaces, that is not important. Okay, then another example is liquid solid two phase flow. So if you recall, I gave you one example that in case of thermal power plants we get some bottom ash, and what we do, we allow that bottom ash to mix with water, and once it is in the form of a slurry, then we transport that bottom ash in pipelines. Okay, so typically whenever this slurry will be transporting in the pipelines, that then what kind of different flow arrangements we can have. Okay, so this is the cross section of a pipe, and in this cross section all these gray colored particles you can see are nothing but suspended solid particles. So these are suspended solid particles, and this surrounding phase is nothing but a liquid phase. So this is how it is becoming a liquid solid two phase flow. But in this scenario, if you see, there are two factors. One factor is particles are solid, so one thing will be size and weight of the particle. So because of, if we consider the large size particles, their weight will be increasing and these will try to fall in the downward direction. Okay, and second important point is flow velocity of the liquid. If flow velocity of the liquid is high, then large size particles can also be suspended. But if we decrease the liquid velocity, then the drag experienced by the particles because of the surrounding liquid flow will be less, and particles can settle down because of their own weight. So we have two important things. One will be liquid velocity and second is size of the particles. Okay, so if we assume a combination in such a way so that the size of particle is small, so that their body forces are not dominating and particles are not settling down, and liquid velocities are sufficient enough to keep the particles suspended. In this scenario, what will happen? We will find that all these particles are kind of homogeneously mixed with the liquid. Okay, so you can assume, if you say consider a control volume somewhere over here of this size, and if you assume control volume of same size somewhere here, almost everywhere you will be finding that the number of particles contained within that control volume are almost the same. So it means that solid and liquid distribution is almost uniform across the entire cross section. So this type of flow is called as homogeneous liquid solid two phase flow. Okay. Now I have plotted here two parameters. One is CV and other is UZ. Okay. So what is CV? CV is basically the volume fraction. So if you consider this particle, in this system what we have, as I told you that if I consider the control volumes at different cross section of this pipe, everywhere almost in this control volume I will be getting same amount of the particles and continuous phase distributed. Okay, so if I define volume fraction CV as nothing but volume of dispersed particle divided by total volume of the cell, that is dispersed phase plus continuous phase, that will be becoming nothing but my volume fraction. Is this point clear? And in this case you can see that if I plot volume fraction along y direction, then as the particles are uniformly distributed in the phase, so at each and every location I will be having same value of the volume fraction. So that is why you can see this volume fraction contour is actually having the uniform value. Okay, at each and every point from bottom to top, it is having the same value. Is this one clear? Then second is velocity. Okay, so as the particles are completely suspended, so almost these particles will try to follow the velocity of the liquid phase. Okay, and that is the reason if I consider velocity in normal direction, so this is a cross section, to this cross section my normal will be simply anything normal to the board. Okay, so that is z direction. So if I consider that axial velocity, then velocity distribution will also be symmetric, where maximum velocity is at the center line of the pipe, and as we move away from center line, then velocity will decrease, and finally at the wall, because of no slip condition, it will become equal to 0. Okay, so this is my velocity profile. Now if I do some changes in the flow, okay, what changes if I do? Either if I increase the size of particles, or by keeping the same size of the particles, if I decrease slightly the velocity, then what will happen? If I decrease velocity, then typically the force in the axial direction which is experienced by particles because of the fluid flow, that will decrease, and moreover their weight will try to
interparticle interaction may also increase.
Yes, that will come into play once they are coming close to each other. Okay, that is true. For example, this next situation when particles have come very close to each other, then, and here also you can clearly see that particle to particle gap is actually decreasing. So then also you can see that effect of one particle on other particle will be felt in terms of changes in the hydrodynamics of the continuous phase. Okay, so then here what you can see that the particles will try to settle towards the bottom. Okay, either if I increase the size of the particle or if I decrease velocity, because when I will be increasing the size, what will happen? Weight of particles will be increasing. Once weight is increasing, these will try to settle down. Okay, so other situation can be when particles just started to settle. Once these just started to settle, in the bottom portion we will be having more number of particles, and in the top portion we will be having less number of particles. Is this point clear? And in this way, the concentration of the particles near the bottom will be more in comparison to concentration of particles near the top. Similar way I can analyze. If I draw a control volume over here, in this control volume I am having almost 3.5 particles within this. But if I draw a control volume here I am only having 1.5 particle within the same size of control volume. So it means that in the bottom portion concentration of the particles is, or volume fraction of the particles has increased, and in the top portion it is less. Moreover, if you see in terms of velocity, as in the bottom portion more number of particles have accumulated, so liquid inertia will be slightly decreasing. It has to carry more particles. So that's why the velocity profile will become asymmetric, where maximum velocity is achieved somewhere above the center line, and velocities are high in the top portion and low in the bottom portion. Is this point clear? But still, in this case, particles are not enough close to each other so that their individual interactions are to be accounted for, like particle-particle interactions. Okay. In continuous phase, it can affect, but particles are not overlapping with each other. So that is the reason it is called as pseudo-homogeneous kind of flow. Okay. Then third situation can be, here you can see now you have three different types of particles. Red colored particles are those which have simply settled on the surface. These green colored are those which are suspended, but still their interparticle spacings are less, larger than red but lesser than gray particles. And there are some gray particles near the top where their spaces are large enough to each other. So here concentration distribution will be more steep, here gradient will be changing furthermore, and velocities will also become more asymmetric. So this type of flow situation is called as heterogeneous flow. Okay. And upon further increasing the size of particles, we will be finding that the layer of settled particles will be growing in size, and it will be kind of a stratification, clear stratification, where bottom layer is all heavy particles and top layer are slightly lighter and suspended particles. And in this scenario, concentration gradient will be more steeper. In the bottom it is almost uniform and highest, and in the top portions it is less. Now you can see that in this particular portion your fluid medium contained is less. So if fluid contained is less, mostly these are the solid particles. So these solid particles these will be sliding over the pipe surface. So once these are sliding over the pipe surface, their velocities will be least, and above that velocity of the fluid medium will be highest. Okay. And final situation is fully stratified flow. So in case of fully stratified flow, what is happening? All the solid particles have settled at the pipe surface, and in the top portion we have actually pure liquid. So in this case, concentration profile will be something like this. Below this portion it is uniform, and above this it is 0. And now this interfacial shear will try to slide the particles. So that's why these particles are having some low velocity, and in the liquid medium velocity is extremely high. Okay. Is this point clear? So this is called as fully stratified flow. Now these flow regimes, particularly the homogeneous and heterogeneous flows, have some important connection in between the local volume fractions within the pipe and delivered volume fraction of the fluid medium. Okay. So let me define one other parameter. So this is the local volume fraction within the pipe or at any cross section of the pipe, whatever we have defined. Now there can be volume fraction, I can also define in terms of other way. Say let me call it as CVD, where D refers to delivered volume fraction. Let me define delivered volume fraction for a pipeline in the form of Q dot of solid particles divided by Q dot of solid plus Q dot of liquid. So for example, if you have a pipeline, in this pipeline what you will be doing? From here you will be allowing your liquid to flow, and the flow rate of that liquid is Q dot L. And then also you are allowing some particles to also flow with this. So say flow rate of the particles is Q dot S. Is this point clear? So as per this entry level, depending upon the ratios of flow rate of solid divided by flow rate of solid plus liquid, I will be having some volume fraction which we are supplying at the inlet. Is this point clear? Now, if my flow is homogeneous, In case of homogeneous flow, what will happen? Whatever the flow rates we have provided at the inlet, corresponding to these flow rates, all the particles have homogeneously suspended within the liquid, and this has homogeneously gone out. So at the outlet, if I will be measuring the flow rates of the liquid and flow rate of the solid, that will be coming out to be same. Is this point clear? The flow rate at the outlet will be coming out to be same. So it means that my delivered flow rate in this situation will be equal to the flow rate whatever is present within the medium. On contrary, if I consider the heterogeneous flow situation, what will happen here? I have supplied some flow rates, but whenever the flow has entered into the pipe, some particles have settled and got layered at the bottom portion. Is this point clear? And when these particles have layered at the bottom portion, their velocities have decreased. Their velocity is now not identical to velocity of the liquid. Their velocity has decreased. So if this settling and their flow has started at the decreased velocity, what will happen? At this point, I will be getting higher liquid flow rates. Okay, liquid flow rates almost at the same level, but solid flow rate will be going down. So in case of heterogeneous flow, our delivered volume fraction decreases once the settling of the particles start within the pipe. Is this point clear? Okay, so mostly I think liquid solid flow we will be touching very less in our discussion. Maybe if we are touching, we will be simply talking about the flow of a single solid particle in a liquid medium or fluid medium. Okay, so mostly as per our syllabus, we will not be talking about more about liquid solid flows. Okay.
Sir, in partially certified flow and fully certified flow, there is what is the major difference between in velocity profiles?
Okay. In this partial and fully stratified, velocity profile is almost the same. The reason is because in the top portion in partially stratified, these particles, interparticle spacings will be large, and this will be almost behaving like a liquid. On contrary, here also it is almost like a liquid. So there is not much difference. The only difference can come is that in case of partially stratified, the size of this uniform velocity at the center, this will be less. On contrary, in case of fully stratified flow, depending upon the level up to which these particles are settled, this uniform velocity portion can actually increase. Okay. Okay, so again you can refer to this slide. So this is just an informatory slide which will be telling you that if I am having different phase associations, in these phase associations, what are the different applications, and almost in the outer periphery, these all applications are interconnected. So all these categorization of the phases is actually interconnected to each other. But one additional thing you can see over here, in addition to gas, liquid, gas, solid and solid liquid flows, here I have named one more flow as liquid liquid flows. So can you tell me what is liquid liquid flow? Two different components of liquid. If these are of immiscible nature and flowing together, that will be coming under the category of liquid liquid flow. For example, if you take a pipeline, and in this pipeline if you allow to flow water and kerosene together, so water will be at the bottom portion and kerosene, because of its low density, can be at the top. However, it will not always be true. Depending upon their phase velocity, they can even vigorously mix with each other and form a dispersed flow kind of situation. But here you can see this interface will be continuously changing with space and time when two liquids are flowing each other. So here you can see both the substances are in liquid state only, but they are forming interface. Okay, and this type of flows are majorly useful in oil refinery. Okay, because in refinery, whenever you extract the crude oil, okay, so it is not in the finally in the form of petrol or diesel. Okay, so crude oil is having several other components associated with each other. So when we segregate these components and allow these to flow in pipelines, these settles depends upon their density, and then they form multiple interfaces. Okay. Again, you can see the applications of multi-phase flows. So this is again, you can refer to slides just for your information. Okay. Okay, then comes one important aspect, that multi-phase flow is counterintuitive. Okay, so what is the meaning of this? Let's try to understand with the help of two examples. So one simple example is given over here, where you can see that this is a droplet, sorry, this is a bubble, this is a gas bubble, and gravity is acting in this direction, and this gas bubble is actually rising in where? Upward direction because of the buoyancy force. Okay, and in the surrounding I have some liquid, and these liquid and gas viscosities are in such a way so that their viscosity ratio is 10, and Galilei number, what is this non-dimensional number? I will explain this to you later. This is 100, and bond number is equal to 50. Okay, so these are the important dimensionless parameters which are maintaining the magnitude of the commensurate relative forces in the constant ratio. Okay, for both situations. So now here you can see when this bubble is evolving, how its shape is changing with time. Now, if I consider the reverse situation, that gas phase I have taken as a continuous phase, and I have taken a droplet of liquid. What I have taken? I have taken a droplet of liquid, and I maintained the same thing. Viscosity ratio is also same, bond number is same, Galilei number is same. What will be our expectation? Of course, expectation will be that drop is heavier, so it will be falling, and while it is falling at different time instants, it should also deform into same inverted shapes. Okay, so we will be expecting that, say, drop should again at t equal to 3, it should get shape something like this. Then at t equal to 4, it should get more thinner, something like this. So kind of inverted shape should come. So that is our normal expectation. Okay, but in reality, if you see, these are the shapes which we will be obtaining. Okay, so from this point we can understand that these shapes are actually completely different. So it means this is counterintuitive. Now can you tell me what could be the reason for change in shape? Because relative velocity should remain same. So if relative velocity is remaining same, then ultimately the drag force and because of viscosity ratio and because of the bond number, the gravity and buoyancy forces should remain same. So what is the reason? What could be the potential reason? One potential reason could be when it is in the gaseous phase. So gas has low viscosity. Okay, so when it will be rising in upward direction, there will be formation of some internal circulations within the gas bubble. Because of its low viscosity, we will be finding that if we analyze the flow within the bubble, within this bubble there will be formation of some internal circulations, and these internal circulations will try to create some additional stresses, additional viscous stresses, so that the internal shape of the bubble should not deform much. To deformation of bubble, these will be providing some resistance. Okay. On contrary, because of high viscosity of this liquid medium, these internal circulations will not be there within the liquid. So as there is no internal circulation, so it means internally there are not much stresses. Okay. So that is the reason from internal side this liquid droplet will not be feeling any resistance to the flow. Okay. So maybe at the moment you will not be understanding this. So this is corresponding to some specific size, and other thing is this particular situation is in a confined medium. Do you understand confined medium? Means say you have a tank, but whenever you are talking about the rain droplets, so there you do not have anything confining them. Okay.
Sir, why are there portion of internal circulations due to the viscosity difference? Internal circulation की बन रहा है viscosity different है.
Whenever you have low viscosity, what will happen? Fluid will be having easy mobility. So if you have gas bubble, so say your some interfacial shear is acting over here. So that interfacial shear will be finding less resistance because of the internal viscosity. So because of this interfacial shear, what will happen? These gas will start moving. But here, if you have same amount of interfacial shear present, but the medium is having high viscosity, then will it rotate? So that is the reason. Okay. For example, you can consider that you have this room filled with gas. Now in this room, if I take a horizontal plate and if I move that horizontal plate in this direction, I will be finding that in the gaseous medium there will be velocities up to the significant portion. But if I fill this up to this level with water and then if I move a horizontal plate with the same velocity, in water the penetration of velocity will be up to, okay, so that is the, because they are dissipation. So that is the reason that once viscosity is high, then the internal circulation, interfacial shear will not be sufficient enough to produce the internal circulation, overcome the viscous stresses. Okay. Then one another example is, so if you have say a tube which is filled with liquid, and in this tube if you have a gas bubble of this type, so of course because of the buoyancy force it will be rising in upward direction. Now if I start tilting the angle of this tube, what will happen? Velocity should increase or decrease. See, if you have a pure horizontal pipe, in pure horizontal this will get just accumulated at the top, so in pure horizontal it will be 0. Okay. If you keep on increasing the angle, velocity will keep on increasing because the magnitude of component of buoyancy force will be increasing. Okay. So as per this intuitive approach, whenever it is reaching the 90-degree angle, then buoyancy should be highest and velocity should be highest. But if you do experiment, you will be finding that whenever angle is somewhere close to 75 degree, then it is this, and if it is 90, then it will be further less. What is the reason for this? And somewhere close to 45 degree, you will be having the highest velocity. So typically, whenever a bubble moves, buoyancy force is responsible for rise of the bubble. But there is one more force which is balancing the buoyancy force so that bubble should remain at the constant velocity, and that force is actually drag force. Buoyancy is because of gravity. So weight of bubble is lighter and it is rising. Okay. But what other force will be coming into picture? Drag force. Okay, drag, because see, when this bubble is rising in upward direction, what is happening? Tube is closed from both bottom as well as from the top. So this bubble is going up. So this much volume should be, this much volume of liquid should move from top to down. So liquid will be counter flowing in the downward direction and in the form of a thin liquid film. Okay. So of course, when this thin liquid film is moving down, it will be producing some amount of skin friction drag, and because of the shape, some form drag over this. So ultimately, drag force will be acting on the bubble. Okay. Now, what will happen? This drag force will be balancing with the buoyancy force. Then only I will be getting some constant value of velocity. Okay. Whenever my angle of the bubble is angle of the tube is 45 degree, then shape of the bubble is such that so that it experiences least drag. So that is the reason that buoyancy and drag are balancing in such a way. These are balancing in such a way so that we are getting highest velocity corresponding to 45 degrees. Is this one clear? At different angle, you can see here shape of bubble is different, here shape of bubble is different, here shape of bubble is different, because bubble is a deforming substance, it is not a solid entity. Okay, so bubble can easily deform. So once bubble is deforming, it will try to occupy a shape of least drag force corresponding to an angle of 45 degrees, and that is the reason at 45 degrees it is having highest velocity. Okay, but this is something which from our common intuition we cannot think. Okay, from intuition we'll say that velocity should be highest when angle is 90. So that is the reason, because of the presence of deformable interfaces between the two-phase or multi-phase flows, we will be finding that their fluid dynamics or understanding will be becoming counterintuitive. So that is the reason these type of flows are actually difficult to analyze. Okay, now with this initial basic idea about multi-phase flows, now we will try to understand more into the multi-phase flow models and notations. So let us first talk about that if we have to analytically or numerically solve the multi-phase flow problems, how we can define our problems and what type of models we can use. Okay, so if I am having disperse multi-phase flow, what is the meaning of this? What is the meaning of disperse multi-phase flow? You should be able to predict now. Say I have a tube. In this tube I am having some particles which are distributed within the continuous phase. So this will be coming as the type of nothing but dispersed flow. Okay. So these are particles. Now particles can be of two types: solid particles and fluid particles. Okay. Mostly if solid particles are there present in the flow, these will be rigid and non-deformable. Is this point clear? And fluid particles can be of again two types. If my continuous phase is liquid, then these will be gas bubbles. So these particles will be then gas particles. And if continuous phase is gas, then these will be my liquid particles. Okay. And typically the fluid particles will not be rigid and these will be of deformable nature. Is this one clear? However, below the certain size of the particle, if I assume that size of fluid particle is very less, then below certain size of particles, if their non-dimensional parameter, okay, say Weber number is less than 5, then we can assume their shape to be almost spherical. Okay, that's something different, we will talk about it later. So this point is clear. Now if I have to model these two situations, I can model these two situations in different ways. Either I can use the trajectory models or I can use two fluid model. Now we have to understand the difference between trajectory model and two fluid model. Let us first talk about the trajectory model. First, can you tell me what do you understand by trajectory model? Trajectory, the word itself is giving some idea. If I consider a particle, okay, and say it is changing its position with space and time, so what will happen? If I try to analyze it in such a way so that I can determine its velocity and new position, I will be able to determine its trajectory. So this type of model is something which is referred to as trajectory model. Here, for each particle, we will be solving its governing equation. Okay, and by that governing equation, we will try to predict its position and velocity, so that we can then from the velocity we can determine next position. Okay, so here for individual particles, if I am solving the equations, that is coming under the category of trajectory models. And trajectory models are particularly useful when we talk about rheology of granular flows, because granular flows will be almost solid non-deformable particles. So analyzing trajectory models for such type of flows will be useful. Okay. Then comes, so the difference is that if I use trajectory model, then for each and every particle I have to solve separate its governing equation. Okay, so equation of motion for each and every particle will be solved independently. Second approach is two fluid model. In two fluid model, you can see the dispersed phase is treated as second continuous phase intermingled and interacting with the continuous phase. So what is our assumption? Our assumption is that dispersed phase is also a second continuous phase, but this is intermixed and interacting with each other. So it means that whatever the different particles I have drawn over here, I am combining all these together, and their combination I am referring to as a second continuous phase. Is this point clear? So all the particles I have combined together to form and assumed all these to be a second continuous phase. So if this is the case, now in your flow domain, how many phases I am having now? One continuous phase and one dispersed, that also I am calling as a continuous phase. Is this point clear? Dispersed phase also I assumed as a second continuous phase. Now, for this continuous phase, I will be solving one continuity and one momentum equation. Say if I am talking about adiabatic flows, I am not considering the energy transfer. Okay, and here also I will be solving one continuity and one momentum equation. Okay. However, whenever I am solving these individual continuity and momentum equation for two different continuous phases, ultimately these two different continuous phases are also intermingled with each other. So for their intermingling effect, what we will do, in my momentum equation of continuous phase, I will be adding some source term for the forces which are coming because of the dispersed phase, and in other case this will be becoming minus of f of s. So we have to define some interaction forces. Is this point clear? Are you understanding this point? So it means I assumed the two phases, separately solved the continuity and momentum equations. However, to account for interaction between the two, some additional force has been accounted for. Okay. this type of modeling approach we use when our interest is not in shape and behavior of the individual particles, but our interest is to analyze the complete system as a whole. Okay, so say if we are interested in averaged parameters, there can be two types of parameters. One is called as averaged parameter and other is called as instantaneous local parameter. One example could be, if I have a pipe, okay, in this pipe, say my liquid and gas are co-flowing each other and gas is flowing in the form of bubbles. Now if I use some valve over here and similarly one valve over here, okay, so initially these valves are open. Now if I simultaneously close these two valves, what will happen? Simultaneously I have closed these two. So this portion of the tube is now isolated. What will happen? Lighter particles will try to get accumulated at the top. So somewhere over here I will be having dispersed phase, say it being the lighter one. And here I will be having the continuous phase. Now I know about what is the height of the dispersed phase and what is the height of the continuous phase in this column, and if I know the cross sectional area, then what will happen? I can determine volume of the dispersed phase divided by I can do volume of dispersed phase plus volume of continuous phase. This will be some parameter volume fraction. But what is this volume fraction? This volume fraction is kind of averaged volume fraction. Okay, because to certain pipe section I am defining this. But instead of this, if I consider that this is my cross section and I simply take infinitely small thickness across this cross section, and only within this small, infinitely small volume, I measure the distribution of dispersed phase and the continuous phase. What will be that? That will be my local volume fraction. Is this point clear? Okay. So at a cross section, if I take infinitely small thickness control volume, across that whatever my volume fraction will be coming, that will be my local volume fraction. Moreover, because this two-phase flow system is actually very complex. So what will be happening? At one point of time across this control volume there can be 3 bubbles, but at some other point of time there can be only 2 bubbles. At some time there cannot be even a single bubble. So along with the local, this will also be instantaneous, because if you change the time, then also in this infinitely small volume your volume fraction can change. Okay, so this is my local instantaneous volume fraction. On contrary, this is averaged volume fraction. So if you are not changing the flow regime, it means your particles are remaining in the same flow regime, and if you measure at t equal to 5 second or t equal to 10 second, then also almost the same value of the averaged volume fraction will be observed. Okay, so when my interest is not to look into the individual minute details of local instantaneous fields, in that case we can use two fluid models where our interest is just to account for the average flows. Is this one clear? So interaction terms are used for exchanging mass, momentum and energy between the two flows. So I only added the source term in momentum equation because I considered that our situation is adiabatic. There is no mass and energy exchange. But if we have mass and energy exchange, then we have to solve energy equation as well, and we have to also write the mass exchange and the energy exchange term. Okay, now one important point. Ultimately what we have done, all the small bubbles which are distributed within the continuous phase, all these together we have given the single continuous phase. Okay, so here what we need to do, we have to follow some averaging process in order to define the properties of the complete dispersed phase, because it was distributed randomly and at different portions of this particular fluid there can be different properties. So ultimately we have to average it out to make it a single continuous phase. And last is separated flow model, and separated flow models are actually the most generic one. Okay, and in this type of flow models almost there will be rarely any assumption, there no averaging etc need to be done, and typically these are used for situations where you have clear segregations between the continuous and the liquid phases. For example, say water is here, air is here. So in between air and water, the interface boundary is clear. So what I will be doing, for water I can solve separately, for air I can solve separately, and then I can allow some interaction terms for the interface through appropriate boundary conditions at the interface. Is this point clear? So in theory, we must solve the single phase fluid flow equations in two streams, and then we will be coupling them through appropriate kinematic and dynamic conditions at the interface. What will be appropriate kinematic and dynamic conditions at the interface we will discuss in the next class. Okay, and now we'll stop here for today.